In the last part, we hooked up the amplitude and frequency to our noise function to have some more control over the quality of this line that we're drawing. What I'm going to do now is wrap all of this up into a function like what I planned it at the start. I'm probably not going to call it draw noise line, I'll just call it noise line, and I'm going to give it, for a start, I'm going to give it these 4 arguments, x1, y1, x2, y2, and it's going to implement what we've done here. So I'll be able to call this with different x and y values and then have it just draw anywhere on the canvas, which will be very convenient. So let's go into our code, make everything small. And when you're thinking about doing this process of putting something into a function, it's called refactoring. And you should watch the lecture on refactoring where I talk about that process in some detail. So let's think about what parts of this code will actually become a part of the function. So probably those ones are going to be outside the function. So we're calculating some temporary variables there, x1, y1, x2, y2, but we're going to pass that information into the function. So probably from here down is where we're actually doing the function. So that's all going to be wrapped up in a function, and we're going to pass this information in from the outside. So when you create a function, it's not automatic that everything that you've written goes into the function, because sometimes that's actually not giving you the flexibility. If we put this inside the function, that would then fix the function to those points. It wouldn't allow us to draw it at a different point. So let's actually just copy all of this. Okay, and then we're going to just define a function down here at the bottom, function noise line, which takes an x1, a y1, an x2, and a y2. And we put the curly brackets in because we're defining the function, and then we can just paste everything that we just copied out of that other part, out of our draw function, into here. And that's it. Actually, that's all we need to do to define the function. Now that's ready for me to use, and I can just say noise line and give it that information that it needs. So the x1, the y1, x2, and the y2. And that works. So we could actually create a second line very easily by just calling that again, but giving it a different y position. So let's say y1 equals the original y1 plus 100. And y2 equals y2 plus 100. And put them in, and I'll get a second line beneath the first one. Now notice each line is drawn exactly the same way. And if we're drawing a number of lines, we probably want each one to be a little bit different. So one thing we could do is give an argument to our function here after the y2 for the sort of offset into the noise function. So let's say noise off for noise offset, noise off. And my first noise off is going to be, I'll actually add that as an argument here. So let's just say that's equal to 0 for the first one, and noise off equals some big number like 3,000 for the second one. So they're going to be sort of separated in that noise function space. So what we can just do is add that on here when we sample, where our sample point is. We just say noise off plus frame count plus I times the frequency will give us our sample point, and then we sample from that sample point. So because we're passing in a different noise off each time, each line is going to be kind of sampling from a different spot in the noise function. If I run this now, you'll see that the two lines are different. Now what if we wanted to draw them on an angle? So that's a tricky problem, right? So if I put in for my x2 and y2, let's say, I'll just put in the numbers here. So y2 is going to be 300 and y1 is going to be 100. What are we actually going to get when we draw that? So you can see that we've assumed in our function that we're just going straight across, but actually we're going across and down a little bit each time. So there are a couple of ways we could do that. One way we could use the lerp function to linearly interpolate the y value each step so it goes down. But I actually think this is where we want to use our transformation function. So let's actually create now a version of the noise line that uses the transformation functions to make it easier to draw. So I'm going to just say push and pop around our function, pop. So everything, not poop, pop. And everything that happens in here will be kind of reset by that push and pop. So I'm going to actually just translate to that x1, y1. And rather than having an x2, y2, I'm going to say that the argument to my line function should be some length and then some rotation that I want it to be at. So how long do I want my line to be and what angle do I want it to be on? So len is going to be the first one and then rot, or let's say angle. Okay, so we'll translate to x1, y1 and then we'll rotate by the angle. And this angle should be in radians. And then we're going to do our normal thing. So I don't need to define the length. And I still do my segment length. I can get rid of this first part here. So now remember that I've translated to x1, y1. So this is going to be start off at 0, 0. The amplitude and frequency are going to be the same. So I'm going to sort of loop along until I get up to just less than the length. And then the sample is going to be the same. The y offset is going to be the same. And then the x and the y each time are going to be equal to 0 plus I, which is I, and then just the y offset. So we don't need the x1 and the y1. And then we just draw a line from px to py and update px, py each time. And then the last one, line px, py. So this x2, y2, we need to calculate based on the overall length. So that's actually going to be length in the x direction and 0 in the y direction because we've already rotated. So because we've translated to the x1, y1, that's now 0, 0. And whatever that line length is and that rotation is, the length is going to be the x distance and there's going to be no y distance there. And I can actually just rename this from x1, y1 to xy because we're only ever using that one. And let me just say this one is nx, ny. Just so we don't get confused there for next x, next y. And that should be it. Let's try it. So we need to call that now, not with x1, y1, x2, y2, but with xy. So x is going to be 100, y is going to be height over 2. The length is going to be 200. And the angle is going to be, let's make this first one 0 degrees. Okay, so it's just 0 degrees. And then we can call our function with all of that information, x, y, length, and angle. Now let's make our second one to be x, y, Length is going to, let's make it shorter, 30, or maybe longer, 300. And let's make the angle equals minus 30. Let's see what happens. Okay, so now I've got two lines. The first line is going straight across, and the second line is going up on this minus 30-degree angle. So when you define these angles, 0 is straight across, and as the angle goes positive, it goes down. So if you say radians 90, that's actually pointing straight down. It would actually be a good idea if we moved the code for setting the stroke weight and stroke color out of our functions so we can control that from where we call the stroke. So here I could set the first one to be blue, and then I could set the second one to be green. And make the stroke a little bit yeah, so there we've got those two lines. So now we've got a function that we can use to draw anywhere on the screen. We just need to figure out what that length and that angle is. So it might be, this is actually one place where you could use a p-vector really easily. So let's say that we wanted our, we don't, like it's kind of easy to think, like if you're drawing something on a page, like I have here, if I draw 2 points on a diagram, the first one I'll say is like 100, 100, and the second one is 200, 350. That's easy to think about. But then how do you figure out the angle from that first one to that second one? That's a little bit more difficult. And then actually, how do you figure out how long it is between those two? So you do need to do a little bit of maths to figure that out. But one way you can do it is actually just use a p-vector. So let's say that let's go back to that example and say that I want my x1 to be equal to 100 and let x2 to be equal to 100, and let, sorry, that should be y1, and then let x2 equals 300 and let y2 equals 275. What's the length and angle between those 2 points? Well, you can use any of the trigonometry functions, but I actually find it's really convenient to use the p-vector object. It makes this really, really fast and easy to figure out. So I can say let v equals create vector, and it's going to go from x1 to x2, so I just say 300, which is x2, so x2 minus x1. That's the x part of the vector if it points between those 2 points. And then the y part is going to be y2 minus y1. And that's all you need to do to figure out the angle and the length of that vector. So once you've done that, you can say len equals v dot magnitude. So the magnitude of the vector is how long it is, and then angle equals v dot heading. Heading is the angle that the vector is pointing in. So I think that's actually the most easy and convenient way to do that. So now if I draw that line, we should see it go from the top corner down to the bottom right. Now did we get that? x1, y1, oh, interesting. Oh, actually here I need to put x1, y1, just because I used a different variable. Yeah, so that blue line is kind of now going down on that angle. And if I changed y2 to something like 175, my vector will kind of figure out that new angle for me. All right, so that's sort of now taking it into a function form and making it possible to have these on an angle. And you can see the nice thing about using the transformation is that our kind of peaks and valleys are in line with the direction of the line. If we just linearly interpolated along the wire, the peaks and valleys would kind of be up and down, which is probably not what we want. I'll stop this video here, and then in the last one, I'm going to actually connect this up to some sound.